Hi Year 12, we are back with chemistry again, and today we are going to be learning about electrolysis of molten salts. So I'm going to put the whiteboard on and let's get started. Get rid of me and get the whiteboard going. All right, where are we? That's what I want, that one. Okay, so electrolysis of molten salts. So we learned last lesson about what electrolysis is, and today we're going to look at how electrolysis actually occurs and what products you get when you do an electrolysis of molten salts. So the first thing I want to talk to you about, molten salts. Okay, so remember, salt is just another word for ionic compound. Now, in the solid, ionic compounds don't conduct electricity. And that's a bit of a problem, because if we have an electrolytic cell, we need it to be able to conduct electricity. So there's two ways that we can get an ionic compound to conduct electricity. The first of these is by melting it, because when we have molten, we free the ions from the lattice. So we have mobile charged particles. All right, the other way we can do this is by using an aqueous solution. And we're going to talk about that next week. So again, we have the ions attached to mobile water molecules. And again, that means we've got mobile charged particles. Okay, so today, though, what we're looking at is the molten salts. So what you need to understand when we have an electrolytic cell and some electrodes, this is going to be our molten salt. And we're going to connect this up to a power supply. So remember, the long one is the positive and the short one is the negative. So that's the positive and that's the negative terminal of the battery. So remembering what we learned last time, whoops, wrong. Okay, it's actually the anode that's positive, isn't it? And it's the cathode that's negative. So remember, anode, still oxidation. Red cat and ox still stands. And we have reduction at the cathode. Now, if we have a molten salt in there, let's give our molten salt a name. Okay, let's do our first example here. So the first example over here is molten potassium bromide. So let's call this potassium bromide. Now when molten, and we have a little liquid on there. So what's in molten potassium bromide? Well, we've got some potassium ions and some bromide ions. They were in a lattice when they were solid, but now they're separate. So we've got K plus and Br minus. And we've got millions of those obviously floating around in the electrolyte. But we need to think, where is the K plus going to move to and where is the bromide? Because we said that we've got mobile charged particles, but what's moving them? Well, this electrode here is the negative electrode. And so by attraction of opposite charges, the potassium ions are going to go to the negative electrode. And then we have this electrode is positive. And that means that the negative ions are going to go over to the positive, just by attraction of opposite charges. So what we have is our anions move to the anode. I will master this technology if it kills me. And then we had in red our cations moving to the cathode over there. All right, so if the anion gets oxidized, so where's my anion color? Here's my anion color. So my anion is going to get oxidized. So the anion is Br minus. And if we oxidize that, we're going to increase its oxidation number. So its oxidation number currently is at -1. So it's just going to be oxidized to the corresponding element. Oxidation number of 0. So we've got an increase in oxidation number, therefore that's oxidation. Now we need to balance that half equation. We've got 2 bromines on the right and only 1 on the left, so we need 2 there. Now we just need to balance for charge with 2 electrons on the more positive side. So this is what's going to happen at the anode. And this was a liquid bromine. It would form probably as a gas at that temperature, but you know, we'll just write that as a liquid. Bromine is a liquid at room temperature. Okay, what's going to be happening over at the cathode? Because at the cathode, we have our cation, which is potassium ions, and that's going to go to the cathode and be reduced. So its oxidation number here is +1, and it's going to become the corresponding element, potassium, with an oxidation number of 0. So here we've got a decrease in oxidation number, therefore that is reduction. And we need to balance the half equation and put some states in. This is a liquid. Potassium would definitely be a liquid at that temperature. And so the only thing that you need to worry about with electrolysis of molten salts is the anions go to the anode and they get oxidized. So anions to the anode and oxidized over here, and cations to the cathode and get reduced. And the products are always the corresponding elements. So you just go from ion to element. They're some of the easiest half equations you're ever going to write. All right, we're going to try the next example. So write half equations for the anode and cathode reactions for the electrolysis of molten lithium chloride with graphite electrodes. That reminds me, why graphite? Graphite, there's 2 reasons why we use graphite electrodes. So reason number 1 for using graphite is that graphite is inert. That means it doesn't react with anything. It's not going to stop up our reactions. Oh, where did it go? Graphite is inert. And the second reason is graphite has a very high melting point. Ionic compounds have some of the highest melting points, much higher than metals. So metals would melt. Metals would melt at these temperatures. So we need to use graphite. Firstly, metals could also have redox properties that would interfere with our reaction. So firstly, graphite is inert, so there's no competing reactions. because of course if a metal was the anode, then the metal would get oxidized instead. So we want an inert anode and an inert cathode. Doesn't actually really matter for the cathode. The cathode material doesn't take part in electrolysis. And we want something that is not going to melt at these very high temperatures, okay? Ionic compounds, very high melting point. Okay, so let's look at this example here. So write half equations for the anode and cathode reactions for the electrolysis of molten lithium chloride with graphite electrodes. Now, rather than draw the whole cell, what I tend to just draw in my cell analysis is just the two electrodes. Okay, this is going to be the positive and this is going to be the negative. So the positive electrode, remember, is the anode, and the negative electrode is the cathode, just for electrolytic cells. Now down the middle, I write what's in the solution, or what's in the electrolyte. So in this case, it's molten lithium chloride. Molten lithium chloride is Li plus liquid and Cl minus liquid. So I write them down the middle. Let's get the element right though. So I'm going to write Li plus and Cl minus. Next, I work out where they're going to go. Okay, the lithium ions, are they going to be attracted to the negative or the positive electrode? Well, they're positive, so of course they're going to be attracted to the negative electrode. And the chloride ions, they're going to be attracted to the positive electrode. So over here at the anode, we're going to have chloride ions, and remember, we have oxidation. So our chloride ion is going to be oxidized, and the product, always the corresponding elements. So Cl2 plus 2E minus, and of course we need two Cl minuses there. The cathode is reduction. So we have lithium ions, and we're going to get the corresponding element lithium, and balancing that half equation, whoops, try 1E minus. There we go, lithium plus E minus, and we get lithium metal. Better put our states on. Liquid chlorine would definitely be a gas at that temperature. That's a liquid, and that lithium metal being produced will be a liquid as well. So that is the electrolysis of molten salts. I'm going to put up a worksheet with a few more examples for you to try, and I will see you in our next lesson.